Okay, in this presentation we're going to look at discrete random variables and in particular approximations of random variables using other distributions. So what we're going to do here is look at, so essentially let's look at the question. For a certain type of policy, the probability that a policyholder will make a claim in a year is 0.001, which is to say 1 in 1,000, okay? Now, if a random sample of 10,000 policyholders is selected, calculate an approximate, remember that word, value for the probability that not more than 5 will make a claim next year. Okay, so not more than 5, that means less than or equal to 5. That's something to remember as well. So, in the first instance, we would use the binomial distribution to answer this. And the reason is we have a clearly identified value for P, which is 1,000, or 1 in 1,000, or 0.001. And then we have N equals 10,000 policies. So, policyholders even. Now, if you try the calculations, you'll realize very quickly that that gets very difficult to do, even just for one part of the calculation. So essentially what we're going to do is we are going to remember that we are asked to make an approximate value for that. Okay. So what we're going to do here is use the use the Poisson distribution to approximate it. Now what we have to do in the first instance though is justify it. And remember, this should always be part of your answer. Now what I have here is sort of more theory written out. That's not exactly part of the answer for this, it's just general theory. So for when the value of n in a binomial distribution is large, and it's definitely that case here, and the value of p is small, again that's the case here, the binomial distribution can be approximated by a Poisson distribution if the following conditions are met. N is greater than 20, that's definitely the case here. P is less than 0.05. Now in some other textbooks or courses you might get different things like N has to be greater than 50 and P is less than 0.02. So other things doesn't really matter, as just sort of justify it according to how you are told to justify it in your textbooks and your coursework. Okay, the point is not how you justify it, but just justify it. Okay, now sometimes we use much more strenuous conditions as well. NP has to be less than 5 or less than or equal to 5. We actually won't meet that, and we don't meet that. So essentially what I'm going to do here is just ignore that one. Okay, has to be less than or equal to 5. We're at 10. So X is a binomial random variable with sample size 10,000 and P equals 0.001. Okay, X can be approximated by the binomial distribution with mean lambda is equal to 10. So where does that figure come from? The binomial mean equals n times p, which is, in this case, it's 10,000 multiplied by 1 over 1,000, which is essentially dividing by 1,000. 10,000 divided by 1,000, that gives us 10. And that is our value for lambda. Okay? So there we go there. So essentially what we have to do is approximate the probability of no more than 5 claims. So to do that, what we're going to do here is we are going to use the binomial mass function. I just realized some of my numbers are coming out a little bit funny. Anyway, k factorial is what that should read there. So my factorial signs are a little bit messed up. So this is what we're going to use, and essentially what we have to use is we have to use it 6 times. We're not using tables here. If you have tables, great, but we're going to work it out here from scratch. Probability of x less than or equal to 5 equals the probability of x equals 0. Probability of x equal to 1, 2, 3, all the way up to the probability of x equal to 5. Now, what we're going to do here is work it out for each of the 6. We'll work out this calculation here for each of the 6 numbers. So essentially this is the operation that we're going to do, this one here. Now, so essentially, again, the factorial sign's gone a little bit funny there. I don't know why that's happening, but just bear with me. Live editing is great. So essentially what we're going to do here is just e to the minus lambda, just take that out, that's e to the minus 10 actually. So e to the minus 10 by the sum of lambda factorial, well actually let's just do 10 to the power of I over I factorial. Okay, so I will be 1, 2, 3, 4, and 5. Okay, so when I is equal to 0, 10 to the power of 0 is 1, 0 factorial is 1, 1 divided by 1 gives us 1. When I is equal to 1, 10 to the power of 1 is 10, 1 factorial is 10, and so on. So we work it out, 10 squared over 2 factorial plus 10 cubed over 3 factorial plus 10 to the power of 4 over 4 factorial plus 10 to the power of 5 over 5 factorial. Just work it through. Essentially, it's a little bit of calculator work. Essentially, what we do is add up all those numbers there and multiply that sum by e to the minus 10. Whoops, didn't mean to do that. And then we should end up with 0.0671. And that's the answer we're looking for. You should get an answer close to that. Again, rounding error comes into play a lot. So we'll leave it there.